Good morning, good afternoon, good day, everybody. Welcome to this May OpenX Late Year Community Meeting. This morning we have a couple of folks from the Intel TPP project, Renato and Lorenzo, that will be presenting on some of the current progress as well as developments that have been going on TPP side. Renato, take it away.
Thank you. I'm going to try to share the window here. This one. Can you guys see my screen?
Yep.
Good.
Yep.
Okay. I think you guys are still seeing the thing because now the window changed for me. Anyway, so this is a project that it's a research project that we're doing at Intel Labs. These are the names of all the people who work. So this is not like us, just us. It's actually a bunch of people working on this. And the idea in this is that we're trying to solve more or less the same problems that modular, as you probably all just seen, which is, ISAs come and go, and hardware gets more complicated. There's more of it, and if you try to do this in libraries, you end up with a lot of libraries, and none of them work with the next hardware or the previous. And if you try to vectorize or parallelize or shard or whatever, it's never perfect, and it gets even harder when you try to use, the specialized instructions in the new extensions that humans have designed for a specific purpose, so they know exactly what to do. And sometimes it's hard or even impossible to prove that you can do that with just compiler transforms. And then, once you optimize, when you run your optimization, you run this on high-level IR, you don't run this on low-level IR. And then as it goes down to machine instructions, it's just, there's so much that happens in between that you cannot guarantee that whenever you vectorize a loop in IR, you will get the exact sequence of instructions. So this all of the pass ordering problems, etc., is not really a thing that you can easily do with compilers. So if you think of traditional compilers as being at the top, super generic, and the Ninja handwritten code being the most specialized, this is like even below frameworks and generic libraries. This is a Ninja code written by a person for a specific model, for a specific hardware, for a specific problem. So you don't want to be there, because you need to hire people that know a lot about the hardware and the models and the problems and your data. So it's really not feasible. So what we're trying to do is to bring the traditional compilers all the way to the Ninja code without actually having to write the code itself. So there is already prior art. So this isn't like a thing that we just creating right now. There's this paper that was published a few years ago on tensor processing primitives. It's like a high-level tensor ISA that you can, they operate at tile level, not at the element level. So you can dispatch these instructions inside an outer loop and leave how the library is going to implement the inner loop to the implementation. And this should scale to anything that can consume tensor tiles. So any CPU, GPU, the paper implements many machine learning models and high-performance computing kernels using these primitives and in ARM and Intel. So it's something that, at least on the CPU level, it scales well. And we are looking into GPU code generation, but it should be translatable to GPUs as well. Of course, GPUs are more complex than CPUs in how you form the kernels, because you need like larger kernels, less data transfers, etc. But still, the building blocks are similar. So what this is basically operates on tiles. So the compiler looks at the outer loops, and the library, the implementation, looks at the inner loops. So and you have fusion, you have broadcasting, you have support for all of these things in the ISA. This isn't like by any means a complete ISA already written in the document. This is an idea that we have that we think are generalizable in for multiple CPUs and multiple GPUs. And the idea is that each one of these libraries will take the tile and implement for a specific hardware, a specific extension, a specific CPU or GPU, just the tile. So how you call the tiles will affect how the higher level cache and memory is propagated through your model, how you accumulate things in which order, which are the loops that you're going through, if this is column major or row major, if this is sparse or dense. All of these things are in the compiler side that you look, how do you fuse, how do you tile, how do you block these calls. And the inner loop in the library side, you don't really care about any of this. You just say, I have a tile that is 32 by 32, 64 by 64. So you're given a tile size, and then you implement in the most optimal way. And you can do this with JIT compilations. You can do this with fat binaries. It doesn't matter. What matters is this ISA has simple operations like matmul or element-wise or even unary stuff like activation functions. And you then provide the most optimal function for that operation with a number of attributes, right? So in libxSMM, which is the implementation for the paper, it's JIT compiled. It's not even JIT compiled, it's like JIT assembled, right? It's basically, these are the orders in this architecture of the instructions, how you're going to lower this to the different accelerations, different extensions, and then it just like lays down the memory, gives you a pointer, and that's it. First time. The second time, you just already call the pointer as a function, and it's done, right? From then on, it's just perfect execution. Actually, this thing on the right, it has all the existing stuff is on the left. The arrows pointing to the this is a new paper that is just being out this year, and this is our offline optimizer, right? We basically take the tiling and the blocking of the loops, and we run through this part looper tool that gives us, this is the loop order, this is the accumulation order, this is the tile sizes, etc. And then we just rerun, the compiler just reruns this with recompiles with the perfect or at least optimal parameters. So the compiler itself is a tiny thing on the right there. It's the new thing that we're doing, and it is, before these instructions had to be written by hand. So to use the tiles, to use the tile operations, you have to write C++ codes to call the library, etc. And you don't want to do that. The whole point is that you don't do that. So we are creating a compiler, an MLIR-based compiler that is taking from multiple front ends, from Python, TensorFlow, PyTorch, whatever, through, in our case, through IREE, and then we get this MLIR, and then we run block, tile, and fuse. We replace the inner loops with TPP, and then we do TPP optimizations. And then after this, we lower to libraries and link with our runtime, and then run. That's it. It's basically, there's nothing special to this. There's nothing magic. It's just a compiler that does the block, tile, and fuse and use the TPP dialect, right? And these the GitHub links on the right are all of the projects that we so this is the IREE community meeting, right? The idea here is to show how do we connect with IREE. We I want to be clear that this is a research project. This is not a product. This is not part of the one API, one DNN. They have their own stuff. They do super optimized libraries for everything. We are just trying to prove a point, which is that we can take a microkernel implementation written by Ninja people, and we can pass this through the compiler, and we can take a complete vanilla Python model in TensorFlow or whatever that lowers to MLIR. And then from then on, we can generate a sequence of optimized calls to microkernels. So this is the first goal, right? It's just a set of passes that transform lin-out patterns using our TPP dialect. It doesn't have to be in the future, it can be another dialect. But we are using our TPP dialect as the vehicle for this virtual ISA, right? The TPP extension. And it's not CPU specific. It can run on GPU. Well, we haven't run on GPU yet, but we know we can do this on GPU because there's no magic. And it's not Intel specific. It runs on ARM2. It runs on AMD. And it's optimal on all of those platforms as well. But the most important thing is we don't want to maintain any framework, front-end, dialect, compiler, anything, right? All of this, we want this to be not just open source in GitHub. We want this to be in LLVM, right? We want the dialects to be upstream. We want the transforms to be upstream. Perhaps the lowering can be like in IREE or PyTorch, because it might be different depending on how your execution environment is. But this should actually be in those projects, not in our project, right? Because there's no value for us if this is closed in a corner. The value for us is that this becomes then the default for all of the new frameworks, and then we don't have to care about this anymore. We can do research in other areas, right? We have work in progress integration with IREE. We have plans for PyTorch later in the year, but right now it's focusing on IREE because what we're trying to do is to connect our passes into IREE, right? And there's this GitHub project here, which is that is a branch that we have working. It's still work in progress, so there's a lot of kinks in there, but we can build this, and we have a CI, and we can run some TPP tests through IREE, and it kind of works. It's not performing, but it works for now. So basically what this is we have the OpenXLA, PyTorch, JAX stuff on the top. Then that goes through IREE, and all of the passes down to the runtime scheduler that runs on CPU, GPU, in our case, for now, on the CPU, right? So what this is, the purplish passes are ours, and the bluish passes are existing IREE passes. And so what we're trying to do is we're trying to map the left-hand side, which is just TPP MLIR, into the right-hand side, which is IREE plus TPP MLIR. So in the left-hand side, you have this TPP opt, which basically has a default pipeline that you see the lines, the purple lines in between the two tells you this is more or less what we do in TPP opt. Is a tensor, a series of passes, then bufferization, then a memref series of passes, then we do some, we go straight to XSMM lowering, and then we just execute, right? And then we have our little runtime, we have libxSMM, and we use OpenMP for parallelization. So in the IREE side, what we're trying to work out now is what is the order of these passes and how we split our passes to fit the IREE pipeline, and so that we don't destroy the information, and so that IREE doesn't destroy our information either. This is our current issue that we're trying to fix to get actual, packed and blocked and tiled and fused everything through the CPU runner without needing our runner to get multi-threaded execution. Now I will pass on to Lorenzo.
Right. Yeah. So maybe we can. Oh, okay. Let me share them quickly. Okay. So can you see the screen?
Yep.
Okay. Yeah. Okay. So on my side, I will give you a not too deep dive on actually our current pipeline and also a rough idea of the kind of optimization we do. So if you want to discuss more details, I would be happy to discuss them, but I don't feel this is actually the right meeting for that. So as Renato mentioned, our entry point is linear on tensor. And already at this stage, we want to perform some optimization. And most of this optimization we perform are upstream optimization. So we use, for instance, tile and fuse from the SCF dialect, and we have blocking and propagation paths that are also upstream in LINAG. And we want to keep working in this way, at least at the LINAG level. And then below LINAG, we have our in-house stuff, which is fine for us to keep in our repository. But essentially, the plan is the following. So we take LINAG on Tensor, lower LINAG on Tensor on TPP on Tensor. TPP on Tensor is actually a quite recent development, because originally TPP was working only on memref, but then we realized that if we want to do something like fusion memref, it's too problematic, it's too painful. So we actually need to lift again the tensor abstraction. So we have our TPP on tensor, and then we convert TPP on tensor. I mean, we bufferize, we get TPP on buffer, and then we convert TPP on buffer to loop or XSM. And of course, the path we prefer is the XSM path because it's our high performance path. And essentially, this XSM dialect is just an interface to our jitter, which is this libxsm jitter repository. Okay, so to give you a rough idea of the optimization, let's see how actually we optimize or how we lower a fully connected layer. So if you think of a fully connected layer at the LINAG level is just a matmul followed by two generics. So the first generics, the first generic that does an addition on the output of your matmul, and the third generic that does a max operation on the output of the addition. So the first pass we do, which is upstream in LINAG, is the pack and propagation. Essentially, the idea behind packing is to relay out your tensors so that you can have better memory access. And in this case, for this simple example, we introduced 3 tensor pack for the input, the 2 input and the output of your matmul. So also notice that usually the pack on the output comes from a fill and an empty and can just be folded with them. So essentially, you can just replace the fill to operate already on your data layout tensor, data layout tensor, and so you actually don't pay the price of this pack operation. And then we have our computation that is expressed in a pack layout, and then a final unpack that brings to the regional layout. So here is important to notice 2 things. So we want to have most of our computation working on the packed layout because we want to amortize the cost of packing, because packing is not for free. It's just memory movement, so it's quite expensive as an operation. So we need to try to push these things as much as we can. So we bubble up the pack and push down the unpack. In our paths, what we have in the repositories today is a set of well-known layout for named LINAG operations. So for instance, for matmul, we have a given packing layout for each operand. The same goes for convolution. So here's nothing magic. It's just we have a fixed data layout that we want to apply, and we apply it on the op. So the second pass that we run is tile and fuse. Also here, nothing too extreme. It's mainly just reusing upstream pass, the SCF tile and fuse. And in this case, also here we have some default. So for instance, for a blocked matmul, what we want to do is to tile the 2 outermost parallel loops. Because if we do that, we expose a batch reduce operation inside the loop, and we have a microkernel for it. So it's really clean as approach. So here we tile the 2 outermost loops. So we map the first block matmul to a BRGEM, which is a batch reduced matmul. Essentially, it's just a reduction around the matrix multiplication. And then the 2 generic get packed based on how you pack the output of your matmul. And also in this case, we get just tile along the 2 outermost parallel loop. And we'll operate on a 2D slice of a 4D tensor. Then we convert linarc to TPP on tensor, and here again we map essentially one-to-one. So the two generic one get to map to a TPP add, the other to a TPP relu, and the blocked matmul is now mapped to a TPP BRGEM. Then at this abstraction, we plan to do additional level of fusion, and essentially here is to also get the performance benefit of fusing in register. So for instance, for this specific sequence of operation, we have a microkernel that does the BRGEM and the addition, they're really all together. And so we also want to run this optimized microkernel. Then we run one-shot bufferization to get to memref abstraction. So SCF4 convert to SCF parallel and tensor to memref. And then right after that, we lower to XSM, which again is an interface to our jitter. Specifically here, each TPP operation gets essentially broken down into two operations: a dispatch operation that gives me the pointer to the function to call, and an invoke operation that actually does carry out the invocation of the function pointer, passing let's say the memref operand to it. Okay, so I think with this I just terminate my short overview of the pipeline, and if you want to discuss more or go more in technical detail, I'm happy to do that after the presentation, and I leave the stage to Adam that he will present some initial results.
So thanks a lot, Lorenzo. I'll be taking over. Let me just grab my presentation then. In one of the windows, let's have a look. All right, hopefully now it's visible to all of you. So now we've seen for the Renato the general overview and of our infrastructure and how the magic happens under the hood as presented by Lorenzo. So now for the actual numbers to show what we can achieve at the moment. Firstly, a quick overview of the methodology that we use for gathering the results. We run on a multi-core system with hyperthreading disabled. All the pre-initialization and post-processing of the results and of the data happens outside of the measurement. So all the packing, the changing the layouts, initializing and consuming the outputs, that's excluded from the measurement. We only focus on the pure computation, as the key to achieving the performance and the good results for our tool is whether we can actually map and invoke the underlying TPP or libxSMM kernels. So here we focus purely on capturing this step. Before we start measuring, we perform a quick warm-up and then gather an average in gigaflops per second over a fixed number of 100 iterations for each kernel that we want to measure. Now let's have a look initially at the high-level example of a 3-layer MLP, just to see where we stand compared to kind of our long-term goal, which is trying to replicate and get to the Ninja level, the hand-reader optimal performance, as it was shown at the beginning by Renato. At the left-hand side, you can see the single-core performance, and the multi-core performance is on the right-hand side. For multiple platforms, here is the general overview. As it was mentioned, the toolchain and the compiler can support multiple different hardwares. So we have both two Intel CPUs and then the Zen 4 AMD, and as well as Graviton Freeze, which is the ARM CPU available at the AWS clusters. For the simpler floating point 32-bit wide floating point operations, we actually achieve the parity or close to the peak performance compared to the handwritten and optimized reference code that's here represented by a TPP offline tuned, which is basically the TPP ISA implemented as through the libxmem API calls, and then further hand-tuned and hand-optimized for this particular example. And here, with the TPP layer, you can notice the results out of our compiler. Both are using the, as briefly mentioned by Renato, the optimization, the tuning using the offline tool, the parlooper, for getting more optimal tile sizes. But the rest is left to the compiler in terms of the automated test cases and further hand-tuned and handcrafted in directly in C++ for the libxmem examples. Now, when you look at the EF16, which is more of an interest nowadays, so the 16-bit floating point representation used widely in the industry in the current AI models, here we still achieve really close to parity, close to peak results for the simpler and older architectures. Well, there's still quite a bit of performance left on table for the Sapphire Rapids. Here, that's due to really take advantage of the newer SIMD units that are available at the newest CPU. You need to apply more specialized, different packing, different layouts for data to achieve the peak performance. This is still something that we have to add as an extension to the compiler infrastructure to actually be able to bring it down, bring it up to this level. However, we're ready. The baseline performance offers quite some commendable results. Then, looking at the multi-core performance, similarly for the 32-bit floating point, the performance nicely scales and parallelizes, utilizing the available hardware resources. And in case of the 16-bit floating point, same, the missing optimization for Sapphire Rapids, the optimal usage of the accelerator units is still lacking. However, the general speed up is still linear, almost linear. Now let's have a little bit of closer look at the more common and different shapes. The previous results were only for the simple fixed example. Here you can see the bit of a more overview. We'll start with results getting on the gem. In this case, the benchmark focus on gathering data only from pure matrix multiplication. And we're having a quick overview comparing to the modular, their initial results that we published recently. One DNN, which is the Intel's, the hand-optimized library or set of libraries and kernels. Our compiler, and again, the hand-optimized, hand-tuned libxmem implementation. As you can see across the board, in majority of cases, we get on-par results with modular numbers, and there's still a little bit of performance ahead left compared to the Ninja code. However, we're approaching around 90-95%. A little bit eyeballing here the precision compared to our libxmem Ninja code baseline. And in general, across the board, still the one DNN, as it implements more specialized, more fine-tuned optimizations, still remains king across the board. For certain layouts, notably as the second and the fourth one, here you can notice a significant drop. Here it showcases that we still leave a little bit of performance on the table. This is mainly specialized compared, so let's say, second result to the third one. As you can see, only the K dimension here is flipped. As Renato mentioned, the paralooper is able to optimize not only tiling sizes, but also the accumulation order and the iteration space. We do not leverage the whole tool, all the information yet in our compiler. Therefore, here we basically drop quite a lot of performance by not optimizing the correct ordering of operations. So hopefully in the future it should be a small extension that will bring us up to the similar performance. As you can see for the Ninja code and 1DNN, the performance for both sizes already implements those kind of operations, and actually it's reasonably similar results. Now, to complete the comparison across the board with the modular results, we also had a look at the fully connected example, FC. In here, it's the matrix multiplication fused together with bias addition and then ReLU activation layer. As expected, the general results, the general trends hold up. The general numbers are just slightly lower across the board. However, the general trends across the compared tool chains still holds similar with the strengths and weaknesses of the current TPP MLAR implementation. Notably, here the second and fourth kernel still not optimizing, not utilizing the correct ordering. Yeah, if we want to have a closer look or a deeper dive at the results, I think we can take a look as requested if needed. But for now, I believe this will conclude our general presentation, and well, back to you, Renato.
No, actually, that was the end. Yes. So questions?
Thanks for the presentation. I think it's pretty cool. I think there's some commonality in the kind of stuff that you guys are looking at and what we've been looking at without it being a coincidence, because we've been working with Lorenzo. So a lot of these things are pretty directly usable. A couple of things that I was interested in is, like, we've been doing some work on trying to get a good path for calling into microkernels in IREE, and a few things have landed in the upstream IREE code base. I was wondering, in terms of your microkernel dialect that you were proposing, what were you looking for? What we have in IREE right now is pretty much a single op that has the information that it needs to lower to an external function call, and that boils down to just function name and operands and handling the memref ABI in a way that makes sure that you can match the ABI that you're looking for at runtime. So far, for everything that we have for the microkernels, that seems to be enough. If there's a need to move this operation upstream, that's possible. It's just one operation. It's an operation and interface, and we could look into that. But I was just curious, what are the kind of operations you are looking at for the microkernel dialect that you were talking about earlier?
So in general, it's basically just a gem, right? I think the one you're talking about is the MM4D one, right?
That's the overall operation, but that's not the op. It lowers into a generic way to calling microkernel.
Right. Yeah, but it's a similar trend, which is it's just basically a matrix multiply generic operation that runs on the tile. So in that sense, they're very similar. So the first thing is what I said in the beginning is, it doesn't matter that much to us that we use our specific ops and flags and whatever. What matters to us is that we can join the compiler high-level outer loop optimization, graph sharding, heterogeneous compute, whatever, at the same time that we have these microkernels. And we believe that a microkernel approach is more efficient from the compiler point of view than library calls, because like CUDA or whatever, because you end up with you can allow the compiler to build these microkernels into a bigger kernel where you can be more efficient, and the compiler can be smarter about this without really having to go down the the parallelization of like the register allocation and instruction selection level, right? And I think your IREE's goal in the thing is exactly the same. Is the microkernel that you call. So I think with this we are like very much aligned. The main differences we have in our side is that there's a lot of complexity in the libxSMM calls, because there are, once you start adding more models and training, etc., there's a lot of cases that pop up. That you can, because you have the memory in your hand, you can kind of cheat, right? So for instance, some gems are fused. So you call a gem, but you say, well, after the gem, in the tile, inside the outer loop, right? You do this ReLU at the end, or you add this thing at the end, right? But also there's things like, well, if you're returning a ReLU, then you really don't need to allocate a whole new tensor with just the non-zero values up. Where you return, you can return a bit vector or a bit tensor with only the values that have a value, and a 0 where it's 0, 1 where it's the value. And then you can use that in the mask register to load and store and to do computation only on the values that are actually in your bit pattern, right? So this is much more efficient. A compiler wouldn't be able to know this, right? But because the extension gives you this flexibility, so a gem might return 4 or 5 results, and some of them, for instance, some gems, you say, run this gem for training, and then it gives you the result in the straight layout and then in the transpose layout, because you already have this in memory for your backward pass. So all of these things are graph things that you don't really know, but because your operation returns 4 things and you know what they are, you can then connect with the graph, and then it's much easier for the compiler to say, oh, wait, there's a matrix that is already being allocated here. I can just use that one. And you reshape the graph with those nodes. And now you don't need to vectorize or reuse or transpose and try to fudge later transpose back into a gem that was. So because for us, this is much more, it's where the performance comes from, right? It's where the ninja performance comes from, is the things that people know, oh, I can do this, I can save this little bit of performance here to do later. So what we're trying to do is to say, how can we have an operation like a dialect that allows you to convey those informations, those ninja information, and then, because if you only use like LLVM-IR, then say, I don't know, the function has 4 arguments that are a pointer to the memory. You don't know if it's written to, you don't know if those are return values, you don't know. But MLIR allows you to return more than 1 argument. Perfect. Now you know, right? And it allows you to tell you these 4 return values are these 4 different things. So the compiler is allowed to say, well, then replace this use of all uses of this thing with that other thing that I know is the same thing that you want. So I think that is just on the gem part. There's also on the unary and binary part that there's, for instance, all of the activation functions are operations. They don't need to be, but they are. And for instance, we have binary and broadcast stuff to implement softmax, right? So you can implement a softmax with a simple sequence of unary and binary TPP ops, right? In your case, will be the MM4D followed by a few things, or not in the softmax, but you'll be just like some operations on the tiles, right? And there's also in the future, it's already supported in TPP, but not in our compiler. We have things like called equations, right? Which you give a bunch of those ops, and then you pass this to an equation compiler that will then try to fuse at the op level, as Lorenzo said, keeping things in registers, avoiding allocating temporary tensors. Even in the stack, you try to avoid all of these things. You use the same buffer, etc. There's a lot of tricks that you can do in there. So just a single gem might be flexible enough for all of the gem parts, but all of the other unary and binary in broadcasting, etc., are required for you to give proper meaning to all of these things.
Right. But I think what I was going for is there's clearly a mechanism needed for calling into microkernels, and you guys have developed one that works for your use case, and we have one that works for our use case. Both of those can run into like divergence from upstream because things diverge in upstream. The dependent parts that are needed to connect all of these things might diverge upstream. So it seems like it might be useful to have something that we can have upstream that basically streamlines the process of offloading to library calls. And irrespective of what you're specifically using it for, it's a core piece of infrastructure that is missing upstream, and maybe there is a space to having an RFC that kind of combines both of these use cases into one that works for both, so that this can be done upstream and be relied upon. For IREE's use case, when I first started working on it, Nicholas mentioned we can just do this upstream, but it was not clear. MLIR doesn't have an end-to-end compilation deployment story, so having something that interacts with libraries and runtime is fundamentally hard to kind of stage. But we have two use cases. If there's spaces where we can say this piece of infrastructure is needed in the compiler that we can rely on, and then kind of decouple the runtime aspects of it, I think that will be a stable state to reach for, irrespective of how we use it on different production research projects. So just something to maybe we can sync offline and see if there's a path for an RFC upstream for these things.
Awesome.
Yeah, maybe just to add a couple of things here. So it's nothing. So essentially, also the things that we were building on top of this memref dialect, like this line pointers index, we are basically reusing all these things. And actually, if you really look at how we invoke the library, it's just a base pointer to your memref, let's say A, B, or C, and then a bunch of other, let's say, word flags to configure the library, and a pointer to the invoke operation that we just need to invoke after the dispatch, because dispatch returns us a pointer to what we need to invoke. So
yeah, so there are a couple of foot guns there right away, right, which makes it hard because one, you like, having looked at this in a little bit more detail, MLR doesn't have a way to represent pointers apart from the LVM dialect. So the only realistic way you can represent a memref, a pointer, is basically a memref with an offset. So you need a pointer and offset to kind of make sure that they all go together. It's a very tricky thing to manage. Function pointers are another thing that doesn't have a native representation in MLIR. So if we need to have these kind of things, then we need to have, it's a non-trivial addition, so it needs to be a little bit more fleshed out. So things that we need to take care of if we want to make this work in a way that works for your use case and our use case, and potentially other use cases.
I think that'll also come into the deployment scenarios and what we're looking at, and which might be a broader scope. Although I think like with what you guys are doing, kind of it has the potential to have a lot of different targets on it. And so examples are when there is no pointer at all in your target. If you've got a non-LVMIR target, how can you still represent this stuff even if you're going down that path? And I think a lot of what you guys are doing, I think, would be really, but at least I'm personally interested in using it on some of those non-LVMIR paths. And it would just be interesting to see if there was a way to actually join these things together. So I think no answers here or anything, but I do think it's really cool that we've kind of separately, but somewhat together, kind of evolved these things. And I think what we've kind of ended up with on both sides very similar. It kind of has very similar applicability outside of just GEM, and more broadly in general. And I'm pretty excited to see, if we can get something. Because like the other thing, kind of as you mentioned, Renato, is at some point it would be nice if people who are not either of us, our teams could go and build these things and throw them in and never even have to talk to us. And I think the tricks to getting there are really to make it that this stuff, it just works. If you really want to do the ninja of the ninja coding, then maybe you have to go and mess with some of the internal features. But I think there's a future where this is just another op. People can add it and just move on.
Yeah, the goal is to some new hardware comes along, a startup that doesn't have 100 engineers to write code. This has the one person right? And the person goes there and writes each one of those kernels in the right way, done. MLR does the rest.
And I think the other side, which is really interesting if we can get the ergonomics right on this stuff, is the user side of, a researcher at a university working on a new algorithm wants to go and not Triton style write a whole kernel, but just write, the one thing for this, if I had the way to twiddle these bits in this one way, I could speed up training 2x or something like that. And giving someone the power to do that without having to swallow the whole elephant and become a compiler engineer and become, runtime performance engineer on particular architectures and stuff like that, I think is a really interesting prospect.
And the long-term goal as well is once we make this work on CPU, and then we make this work on GPU, then we should make this work on both CPU and GPU at the same time. So you get a transformer, if you do like lookup, embedding lookup is faster on a CPU than in some embedded IPUs or XPUs or TPUs, right? So, well, why you do one, you do the other. So now you're doing sharding and you're doing, the whole pipelining stuff. You want some parts of this pipeline to be on the CPU, some to be on the GPU, some to be on the TPU, and you don't need to care about any of this, right? So your researcher comes along and says, no, I can make a TPU more efficient here than the GPU, and he just replace that one with the other, done. Now you have, 2 times faster or something.
I think the other interesting thing there that, a lot of what is possible today is done with very big hammers. It's I'm going to rewrite my entire application in CUDA kind of stuff, and heterogeneity isn't quite there. But most of the times when you're dealing with this stuff, it's really about who has the data. And even if it's 10 times slower to do it on the GPU, it might still be worth it because that's where your data is. And moving several gigabytes of data to the CPU just to run something 10% faster on it doesn't make sense. So I think this gives that flexibility of write the algorithm, express the algorithm, and then use a cost model that actually is not just where do we have this currently implemented in mainline assembly somewhere. It's really, really cool. Sorry, I'm just rambling. This is exciting and great presentation. It's really awesome to see the update on the work. It was great to see it the other day at the OpenXLA thing as well. Really cool stuff.
Thanks.
Yeah, no, I agree with all. I mean, this is quite exciting. Sorry, Stella?
Can I just ask the Ghosh top level question? Like, what are we doing with this other than trading presentations? What are the concrete plans?
Do you mean on your side or on our side?
Yeah, open question to produce an awkward silence, since not moving is the natural state of the world.
I think at least Mahesh and Benoit are pretty much like we're at kind of the last bits to get this all wired. The microkernel path that we have, which just bottoms out on function calls, with plugins statically or dynamically loaded or statically linked into the compiler artifacts, in a way that I think is pretty compatible with what the TPP stuff is doing. So I think that is imminently landing, and I think it would be useful to then maybe get a good brainstorm between us, walk through IR examples on both sides, and just do the sniff test on are we at a point where we could start to talk about some convergence here, or are there a couple more rounds of iteration as we go through that?
Yeah, I think plus one to what Ben was saying, the plugin mechanism already works with the way the microkernels are wired in today, so we can try to use libx, whatever microkernel you're causing, as a way to kind of hook into the IREE compiler and see if that connects and if there are anything that we've missed in the path that we're looking at, and that would probably be the first step to shake out some of the details before. I really think this needs to live upstream because it does rely on some parts of the upstream code base that's not really trivial for somebody who's just entering this. So it might be better to put that all in one place. So that would probably be the next step. So I can give you pointers. I landed that change yesterday. I can give you a pointer to a sample that basically calls the microkernel from a compiled. Like you take an MLR function that calls into your microkernel, and then that's compiled, and you link the microkernel implementation, and that works now upstream in IREE. We can see if that is useful for it, what you guys are using it in TPP, so that you can kind of maybe rely on that or adapt that to reduce the amount of changes you need to make on your side to IREE to make it work, so that it can more harmoniously in the code base.
So I do have a question for the IREE folks. You are implementing more or less the similar things that we're doing, you know, some dialect that then lowers to some library call, etc. But long term, if you don't want to have, you know, monolithic going to SPIR-V for GPU stuff and then just some code generation on CPU, you might want to use optimized libraries from ARM or from AMD or from Intel or some other. So do you plan to have this plugin just like, say, I can put like libxSMM that implements your MM4D op in a way, and then you just have some, you know, local lowering to say, this is how I lower to libxSMM from these ops. And then, because then it will be like pretty much what we're doing, right? It's just like multiple libraries underneath and then some compiler on top.
Yeah, I think, you know, the example of the MMT4D we have is, it's at this point, I don't even know if there's an op for it.
No, there isn't.
So what we've been really trying to do is base this kind of like a fancy, you can think of it almost like a fancy function call. So a function call that is aware of destination passing style and, you know, tiling interfaces and stuff like that. But at the end of the day, what it does end up in before we even go to LLVMIR is a func.func and a func.call. And everything above that, all the microkernel op is really just about how to take, you know, bridge the world of tensors and bufferization and memrefs with their offsets and things like that, and get those into a func.func and a func.call. And once we have that, then everything is kind of uniform. And so the idea then is, because that is all happening above a backend level, like before we go into LLVMIR, that we can use that same mechanism of some op that participates well with linalg and bufferization and tiling and all that stuff, and turn it into a func.func and a func.call, whether that is in an external bitcode file on the CUDA side that is linked into the binary, or a dynamic library loaded at runtime, or, you know, a .o file linked in, or whatever is kind of a separate concern. And so I think, you know, we're really focused on the mechanism. The set of ops, I think, is completely open-ended, just like anything you would put on the end of a call. And what that means then is that if there was a standard, you know, set of compiler transforms that did, say, MMT4D, or you know, what you guys are working on with your gems, you could completely decouple the implementations of those. You know, is it a .c file that was compiled to a bitcode that is linked into the CPU backend for a particular architecture? Was it a pre-written SPIR-V kernel, you know, or SPIR-V function that was linked in? Those become completely separate then from the compiler transforms that might be doing it, and hopefully make that, you know, much easier, an actual API as opposed to, you know, a vertical slice through the whole thing where you need one paired set of things. That's the plan. You know, it's not there yet. The hope, at least from my perspective, is this op, as we add more interfaces to it, you could come in at the very top level. Like, you could have TOSA ops and HLO ops and linalg ops and these ops all together, and they would be partitioned and distributed and kind of spread around the program. We need some more interfaces to make that happen, but that's the eventual, at least my eventual goal. We'll see. See how that goes.
Yeah, we are kind of reinventing a bit the wheel in the TPP on tensors thing, because now we are do bufferization of our ops, which should be similar to the ones in linalg. Although we know the semantics of things, right? So we can assume and create less allocations and less copies and stuff. But we also, you know, thinking about a TPP group, which then will be our fused stuff. But I mean, TCP has the group thing. Is that the same thing? Is that the same level of abstraction? I don't know. So I think there's a lot of design in that space that we need to just try and fail until we find something. Which I think is good that you guys are also looking at the library side, because then these things can happen at different levels, right? A team can look at the ops, another team can look at the library lowering, and this can be slightly disconnected. And IREE can generate XSMM calls, and TPP can generate IREE calls. I think we we can mix and match there more or less independently.
Yeah, and I think at least a lot of the stuff, the nice thing here, starting at the bottom, like given that there is so much precedent for linalg and the lowering levels from that. Now we're kind of starting from the bottom and working our way back up. What do we actually want those to connect to at the bottom here? And so I think the long-term vision of what these look like at the very high level of stuff is something we can kind of we at least are trying to work back up from that. And I think what's nice then is once we have that, once we have the ability to call functions with certain parameters and buffers and stuff, it's done, and we won't have to look at it again, which is always a really nice thing.
So okay, so still a lot of cans and whatnot. What I would love to see at some point is a what would the concrete benefits on different platforms be of a deeper integration, and who's doing that, and what the what the work plan is. I know that's a lot for one community meeting and whatnot, but I'd love to get crunchy about this someday, for things that have concrete benefit, and start really getting that.
We have one concrete step that we want to do, which is in our IREE fork, which is we're gonna spread our passes with IREE passes, and we want to have the packing and the tiling and the TPP calls with acceptable performance. And this is our current end-to-end goal. Once we have this, then we're going to send you guys, look, this is our work. How can we move this up to IREE?
Right, gotcha.
Like a proper thing that you guys can work on.
Okay, so additional performance spikes, and then proof in the pudding, integrate it well, kind of thing.
Yeah.
Well, and with that, everybody, unfortunately we're at time, so let's take some discussion offline. For folks into Euro LVM, I'd be happy to meet up there. Else we'll have our next community meeting in roughly a month, and the next OpenXLA project meeting in, I think, about 2 weeks from now. Thanks, Renato, and everybody for presenting. We enjoyed it quite a lot today, and looking forward to hearing you more.
Thank you.
All right.
Bye.
Bye-bye.
Thank you. Bye.